All right. So a certain high school has decided to offer an SAT prep class again this year. It will offer two different formats, an online or classroom teacher. Counselors want to know which teaching format will yield higher SAT scores, so they have allowed us to set up an experiment. So 50 students have signed up to take some form of the SAT prep class. Draw an outline. Okay, so how many students do we have? 50. All right, so we got 50 students, and then we're going to randomly assign them. Okay, and then we're going to break them into groups. So group one, and then group two. Okay, and you always want to state how many people are in each group. Okay. If they told us like 55 kids, what you want to do is roughly make these equivalent. Okay, so if you have like an odd number, you want to make them roughly equivalent. Yeah, you can't have half a person. I mean, I hear you. It sounds like a great idea, but all right, we got the online prep course, and then we also have the teacher prep course. And then you're going to compare the SAT scores. I feel like this question is pretty easy. You're just like showing the flow. Don't get this question wrong. Like this is too easy. Now, I want us to be familiar with these words. Completely randomized design. Okay? Because we stated random assignments, completely randomized designs. We don't know who's going to group one or group two. Okay? All right. Of the 50 students that signed up for the prep course, 30 are juniors and 20 are seniors. If the counselors are worried that the random assignment could potentially put all the seniors into one of the treatment groups, why would this be a problem? Say it again. Okay. So if this treatment group had a higher SAT, then we wouldn't know if it was because of the type of prep course or because it was full of seniors. It's probably the seniors like second or third time taking the SAT, as well as maybe more of them have had algebra 2. All right, so how could we adjust our experiment to eliminate this potential problem? So we're going to draw an outline of the experiment with our modifications. So they told us that there were 30 juniors and there's 20 seniors. Okay, so we're going to take the 50 people. Okay, so we're going to take the 50 students and we're going to break those kids into juniors and seniors. Okay, and there's 30 juniors and there's 20 seniors. Now what we're going to do is give them a random assignment in both of those groups. And then we're going to break those into group 1 and group 2. And we're going to put these in group 1A and 2A. Okay. And then we're going to look at this one. We're going to call this group 1B and group to be. Okay. And then we're going to assign give them their assignment. So we'll have online, then teacher, then online, and teacher. We're going to compare these. And we're going to compare these. And then we'll compare those. So
Yeah.
second. Oh, JK. Haha. Thank you. Flop those. Appreciate it. All right, so we're going to compare at the end, and then we're going to combine and compare those. So we take out the fact that not all the seniors will go to one specific group. Okay. This is what we call a block design. So we're taking out the fact that, hey, we don't want to have all seniors in one group or majority seniors in one group. Now, the counselors are worried again that the random assignment could potentially put all the super hardworking high GPA students into one of the treatment groups. They have a list of the 50 students and their GPA rank from highest to lowest. How could they use this list to help them set up the experiment? So what you could do is you could pair the top 2 students, then the next 2, and so on, until you have about 25 pairs. And then for each pair, toss a coin. If heads, first student in pair gets online course. If tails, then they get the teacher group. So you're pairing these people up by their GPAs and then randomly assigning them. So this is what we call a matched pair design. Okay, so we have block design, randomized block design, and matched pair design. Okay, go and flip the page. All right, so we're gonna summarize. So we talked about block design. Okay, and a block is where a group of experimental units, we talked about what experimental units were yesterday, that are similar. A randomized block design we're going to separate subjects. All right, there we go. Subjects into blocks and randomly assign treatments within the block. So an example of this was the juniors versus seniors, and then giving the treatments out from there. And the matched pair design, which is the last one that we talked about. That's where subjects are paired up. And then randomly assigned. To treatment. Each subject receives 2 treatments. And the order must be randomized. Okay, a lot of these types of questions are going to be writing an outline. Okay, so let's go ahead and get some practice on that. Go ahead and complete 1, 2, and 3. And then we're going to move on to the next section. So, all right, so you should have gotten, you're creating a completely randomized design to compare the effectiveness of the 3 advertisements. So you got 300 subjects. And then you're going to randomly assign them to the treatments, right? Okay, then you're going to have group A or group 1, whichever way you want to label this. Group 2 and group 3. And then you've got add 1, add 2, and add 3. Make sure that you state the treatment in here. And then you're going to compare all the effectiveness. Good? Yep. You're going to want to state that, hey, this is a group. And you're going to want to say, hey, this is got 100, this has got 100, this has got 100. Yep. This side. It's like, hey, I put these people into groups. Now I'm going to give them whatever treatment it is. Kind of gives you a little bit of a flow. Okay. Are we okay? All right, now we're going to do randomized block design for this experiment. Okay, so the only thing that we're going to change for this is we're going to actually put them into groups first. So we're going to say 300 subjects. And then we're going to split this into older and younger. And we're going to say 150 here and 150 here. And then we're going to random assignment to the treatments. So then we're going to put them in group 1, group 2, group 3. Group 1A, group 2A, group 3A. You're going to do the same thing for down here. Group 1B, group plus 2B, and group 3B. You want to make sure that you state how many is in each group. So it's 50. Okay, and then you're going to say add 1, add 2, add 3, because that's the treatments that they're getting. And then you're going to compare within that group. Compare within this group. And then compare between the two. So if we were talking about presidential candidates, do you think, like, would there have been another way that you did this block? Does anybody block it for something else? Would you block it? Okay. So we're looking at the effectiveness of an advertisement, right? If we blocked it for Democrat versus Republican, would that tell us a whole lot? Because like let's say like the advertisement was for Democrat. Would that really like help you with the Republican Party? Like they're obviously not going to like it, right? So would that be good to look at? Yep. Yeah, you can do that. I don't do more men than women vote? The elderly vote more. Yeah, like young people vote, but like the elderly vote. Like we say we vote, but we don't actually vote. The elderly like get out there and they're like at 8 a.m. like, yes, let's vote. So probably want to look at the effectiveness of those groups. Because everybody who's like kind of in between doesn't really vote that often. So all right. Why might a randomized block design be preferable in this context? And I think we just kind of talked about it. So this block design is going to help to control age. So block design helps to control age as a confounding variable. Within each block, there will be lower variability of results, making it easier to determine which ad is most effective. Okay. If we did it by political, like demographic, like you're Republican versus Democrat, wouldn't there be a lot of variability in that group? Because isn't there like libertarian, but that's still like kind of like more Democrat side. There's conservative, which is more the Republican side. So there's like the extremes. There's people who kind of like live in the middle, like they're Republican, but they're like slightly Democrat, depending on like what they're talking about. Does that make sense?
Exactly, because as you said, like if it's a Republican candidate, then and there's one advertisement just like you go to that, then it's not gonna have a good viewing. Even if like the target audience, it would be a good advertisement. So I think it's still good to block this based off the picture. So
Yeah. You could do it that way. You could. Yep. Yeah. They always give you that survey, right? So these are fake people. So there was John and then there was Jennifer. So half of you got Jennifer and half of you got John. Okay. Immediately y'all started yelling out names. I was like, shut up. But it's okay. It's fine. All right. So your class should perform a modified version of the famous John-Jen study conducted by researchers at Yale. You will now perform calculations with the resulting data and investigate your findings. Are if your findings are I'm trying this again. Statistically significant. So the resume you evaluated was fake. Sorry. Did y'all like John or Jennifer?
Pretty good.
Yeah. All right. So each resume the class evaluated was completely identical, except for the name. Okay. So the first name of the applicant, half the class received a resume with the name John Miller, and the other received one with Jennifer Miller. Let's see if the name alone was enough to influence the hireability ratings. Okay, so we're gonna fill this in, and hopefully, like, you didn't just like everybody circle 4, Hopefully not everybody did, but okay. All right, so for John, we had a 5. For Don, we had a 5. For Jennifer, we had a 5. For John, oh my God, did y'all all circle 5? Oh my God, no. Oh, y'all are the worst. I might not be able to use y'all's data. Yep, can't do it. No, y'all all put 5 or 6. Not even kidding. No. Okay, I'm throwing out your data. Yeah. Y'all are terrible. Y'all didn't even read it. Okay. All right. No. I'm glad I have backup. Okay. But like, all right. They have math experience, but so does like everybody in the world because everybody's taken math at some point in their life. Great.
Nature and psychology and John.
No, this is not mine. Well, but you're hiring for math and they have a psych degree.
Okay, but they have good.
I mean, okay, yeah, psych uses statistics, but not the same. Right. Yeah, you put in a 3? Yeah. See, all right, she's got my back. The rest of y'all, 5s. Okay. Yeah, there was a couple that were like out there, but it's okay. Most of you put a 5, literally. All right, so we're gonna fill this in with some backup data because y'all, I mean, like literally, it was all 5s. It's fine. It's fine. Okay, so go ahead and fill this in with the correct data. The optimum data.
No way. Oh my God, it's you?
Listen, I personally would not hire that person just based off the paper. That's just me. But I was also the teacher over at South. And so like I got to see the resumes of like people who've been in it for a hot minute, people who hadn't. And like, maybe she might be a good educator, but now I will say this. GPA in colleges is different. Yeah.
No, but that part connects with everyone that is looking at the paper. They're like, oh, my gosh.
All right. Let's calculate John's mean. So we're going to add up all these numbers and we're going to divide by how many numbers there are. Okay, so that's going to be 5.33. That's going to be X bar 1. Okay, for Jennifer's mean rating, she got a 4.07. That's going to be X bar 2. So, right? So the difference between these two, 5.33 minus 4.07, which is 1.26. So the way we found that is we subtracted the first mean minus the second mean. We actually had somebody do this at South. They like turned in like a male resume, but then they came in and they were actually female. And I was like, yeah. I was like, you're not Andrew. Yeah. What's up? Bring it to me. I'll pick it. I didn't mean to test one. Oh yeah, I could get that one. There we go. All right. So is the difference between these means ratings statistically significant? That's the question. Okay, so then what we would have done is we would have ran a simulation, which all failed me miserably. I'm not kidding though, it was like all five. Yeah. I printed out all that paper for nothing. Okay, there you go. Right. Oop, here you go, babe. Right. So let's say, are you not done? Hey, we ready? Because we got lots to get through. Let's go. All right, so if we were to simulate this, we're going to use index cards to represent the different ratings in this experiment. So on each card, we would write one of the ratings listed in the table above. Oh, my bad. For both John and Jennifer, for example, if there were 8 ratings of 3 above, then there would be 8 index cards that should have 3 on them. Okay, again, this is what we would do if y'all actually gave me good data. Shuffle the cards and then deal them into 2 piles. This is going to represent the randomly assigning the ratings to the 2 named groups. So, because y'all all put 5s, literally all put 5s. I already got it filled out. It's fine. Y'all already wasted paper. It's fine. Okay, so we're gonna fill in the table. All right, we're gonna fill in the table. So this is after we've taken the rating and we've sorted it into 2 groups, and now we're looking at that data. Okay, so 7, 4, 4, 3, 3, 6, 7, 7, 5, 6, 7, 7, 4, 5, 4. And on the next one, we're doing 4, 2, 5, 5, 6, 2, 4, 4, 5, 4, 5, 5, 2, 3, 6. Not funny. Okay, so now we're gonna find the mean for each group in the simulation and subtract the means. Okay, so again, reminder, we did our ratings. I took your rating numbers, I shuffled them, I put them into 2 stacks, and these are the ratings that we're giving John and Jennifer. We're simulating it. We're trying to determine whether that name change actually is like the reason why he got a higher rating. Yeah. Okay. All right. So if we find the mean for each of the groups, so flip the page. For John, we got 5.27. For Jennifer, we got 4.13. And so if we subtract those 2, 1.14. Now, let's say that each person in here did that simulation where you took the 30 cards, you divided into 2 groups, and then you looked at the ratings for John and Jennifer. Does everybody get it? Yes. Do we understand the simulation? Okay. So let's say that we all did that in here. We would create a dot plot, right? And make up some stuff for y'all because I don't trust y'all anymore with the studies. Okay. We're going to create a dot plot based off of that data. So the difference of your means. So the 1.14 is going to go on the dot plot. Okay. So let's say I pulled that data from you. This is what the dot plot would look like, roughly. Because y'all apparently all want to put 5 as your answer for both. You're like, yeah. Say again. Because let's say that Jennifer got more than John did for a mean. Because remember, our mean is John minus Jennifer's average. Can't believe y'all messed that up. I'm like caught up in it, yo. Y'all would hire anybody. You're like, yeah, that's fine.
Oh.
Yeah. Uh-huh. 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 She what? She did what for 4 years? That is true. Listen, if you've ever worked in fast food, you know. You know. That's easy. Yeah. Class result. Sorry. My bad. It like spaces out and then it's like, nope. I'm gonna transfer it to an iPad. So my handwriting is not terrible. Hurtful. Okay. All right. So what does each dot represent? Each dot represents one simulated random assignment. And the difference of mean rating calculated for two groups. Okay, so how many dots do we have in total? 7, 8, 9, 10, 11, 12, 13, 14, 15. So we have 15 dots in total. What percent of the dots are equal to or more extreme than the difference in means we found in our experiment? So we found this one right here, okay? That was 1.26 from our experiment. So from the original, we were 1.26. So how many are at or above that mean? 1 out of the 15. Okay, which is going to give us 0.067, which is 6.7%. Everybody see how we did that? Okay, so we said there's 15 dots. And there's one dot that's above or at our class rating that we got from the original. We good? All right, so interpreting this percent. So assuming, I'm going to put it on the side because nobody can see that in the back. Okay, so we're interpreting. So assuming that gender does not affect ratings, there is a 6.7% chance of getting a difference of means greater than or equal to our class result. And this is all purely by chance due to, random assignment. This is the long interpretation. So assuming that gender does not affect the ratings, there's a 6.7% chance of getting a difference of means greater than or equal to our class result, purely by chance due to random assignment. So do you think the difference between mean higher ability ratings we found from our experiment is due to the name Or has it occurred purely by chance? So do you think the difference between mean hireability ratings we found from our experiment is due to the name, or has it occurred purely by chance? What do you think?
There's something about like finding a p-values and p-value is above, not above 5% is statistically significant, so it's not like don't happen by chance.
So we could say maybe on this one, but yes, you are right. Okay. The class result could have happened, result could happen by chance because it was 6.7%, but it's not likely. And just like what Nova was explaining, it's less than 5% is statistically significant. So like we were close, but we were off by 1.7%. Now, maybe if we would have done more, we might have gotten a smaller percentage. Yep. So if like your true experiment result, if you look at the data that is above it, what is the percent that have that occurred? So we had the 1 out of 15, right? Okay, so that was 6.7% that had it more. Yeah. So if it would have been less than 5%, then we could have said, yes, absolutely. That gender definitely impacts it. Yep. David? It's finding the difference between the averages. So so you're comparing their averages. You're comparing their averages for the ratings from the resume.
But how are you comparing your averages if you just scrambled the data in order to?
Because you're simulating the experiment over and over again. You're saying, hey, take all these numbers and let's just say, hey, group them into 2 different groups so that we're not going, hey, this is John, this is Jennifer. We're separating them, randomly assigning those numbers, and then looking at the mean.
What if experiment like that, then how would you do like how's that happen? Because if you're randomly dividing the stuff, then it should just be a random assortment of dots. Well, not a random assortment of dots, but it shouldn't be able to show, at least in my mind, it shouldn't be able to show that, hey, this is like there's a chance of this being more likely or something. I don't see that.
So if we would have taken the name off the top, like if we would have just like covered it up, you didn't know the name, would you still give the same rating that you did? Are you sure?
I mean, look at the name.
Okay, so then I can take your rating and I can give it to Jennifer then, because it doesn't matter, right? That's what we're trying to prove. Does it matter? I can take your rating and I can give it to Jennifer if gender does not matter. We're simulating that experiment over and over again because you just told me that gender shouldn't have mattered if I would have blocked off the name. So that rating is going to stay the same no matter whether you give it to Jennifer or John. So we're going to simulate it over again to make sure that that gender doesn't impact it. I'm going to try to do another experiment like this before the end of the week, where y'all actually give me real data. No offense. Yep.
Whenever you do an experiment, it's okay to say that your data is wrong now.
Y'all's data was, but because like I mean, literally, like if we would have calculated this, we would have gotten 5 for the entire thing. No, it was bad. Y'all would have hired some chick off the street or some dude. It's bad.
Right, like, I'm fine.
Where's hate for John? No, gender does matter.
Yeah.
All right.
You're taking on, we put fives for both John and Derek. I think you're unsolved. So I feel like the conversation is not matching.
It would have been rough. It would have been rough. We're gonna look at y'all's data. We're gonna run it again. All right. So in the original Yale study, applicants were sent to STEM faculty at various universities for a lab manager position. Among the 127 faculty that were randomly assigned, either Jen or John materials, the mean hireability rating for John was 3.78. For Jen, it was 2.93. Is this evidence more convincing or less convincing of gender bias than the data from our class experiment? Okay, so first, what was the difference between these means?
It's less than the previous.
So it was 0.85. Okay. So is it more convincing or less convincing? All right, so it was less convincing because Yale's difference of means was less than our class average. So 0.85 was less than 1.26, but more convincing because Yale had a greater sample size. So Yale had 127 people do this when we only had 30. Yep.
So, you know, what first question you approach? Like, what would be the more, like, which would be better? Like, say.
It would say both parts. It would talk about both parts. Mm-hmm. It shouldn't have like pick one or the other. All right. Did you say done? We're almost done, I promise. Everybody's like, difference of means is, I don't want to say it's stupid, but yeah. I wouldn't. Yeah. I mean, like, unless kind of like what you were talking about yesterday, like you say like random number generator stands for RNG. Like you give like a here's what it means, and then you kind of shorthand throughout. But I probably, yeah. Again, you want to assume that the person who's grading your thing is stupid, right? That sounds so bad. I should probably phrase that better. Okay, so what we talked about simulation, and that's where we were repeating. Here's your dot plot of doom. Okay, and then we talked about where the actual result fell. Oh, okay, there was only one above it. Okay. We talked about what statistically significant meant. So that means that when results of an experiment are unlikely, so less than 5%, to happen purely by chance. If it's statistically less significant, we have convincing evidence. We have convincing evidence. So if our results would have been, let's say 4.7%, then that's less than 5%. We could have said, yes, gender is the reason why John would probably get hired over Jennifer. Okay. So go ahead and take a look at those questions. Okay. Go ahead and do 1, 2, and 3. Okay. And then we're going to go over it, and then I'll give you a little bit of time to catch up on some homework if you have not started it. So let's talk. So the following is an example of A/B testing, which is a common data science practice among tech and marketing companies. The marketing team at Yelp came up with the 2 new formats for displaying ads on its site, format A and format B. Before deciding on which format to use across its entire site, Yelp wants to test which format would get a higher rate of ad clicks from the user. To test this, the company randomly assigns 50 users to see format A and 50 users to see format B. Format A had 21 users. Click the ad. That little P with like a little like party hat on top of it is called P hat. P hat. Yes. We're going to talk about that later. Okay. Format B had 19 users. Click the ad. P hat was 38%. So calculate the difference in percent of the users who clicked on the ad. So you should have taken 42 and subtracted 38, and you got 4%. Everybody got that one right? Okay, now here's the hard part. In your own words, explain what statistically significant means. Before doing any further calculations, do you believe the difference you calculated in part A is statistically significant? So the difference between these two is unlikely to happen purely by chance. So something has to be influencing it. Does that make sense? Okay, so the difference of percent from the experiment would be unlikely to happen purely by chance. Because the difference is so small. It is so small. We don't believe the results are statistically significant. Okay, so less than 5% means it's unlikely to happen purely by chance. Since it's 4%, then format A and format B are so close together, there's not like that big of a difference between the two. Like, there's not convincing evidence that they're going to pick format A over format B. Yes.
Means that the ultimate base not be by chance alone.
Okay.
That there's
Okay. Yes. Yes. Okay. Now, following the simulation was performed assuming the format A and format B are equally effective. The individual outcomes from this experiment were randomly sorted into 2 groups. So this is like what we did what we're supposed to do with the resumes on the index cards. Like if I would have put them into two different groups, okay? The percent who clicked were calculated in each group. Then the difference was taken from the two groups. This was repeated 100 times. The resulting differences in the percents who clicked are displayed here. Okay, so out of, yes. Okay, so looking at this experiment, it was conducted 100 times over again. Using the results from the simulation, do you believe the difference in the percent of users who clicked between formats A and B is statistically significant? Explain. So really quick on here, what we found previously is 4%, right? We found 4% for that, the difference. That's right in here. That 4% that we just found, right? Yes, no? That was from part 1. Okay, so using the results, do you believe that it is statistically significant?
Oh.
Why? Because
No. Yeah, okay, look, I've been talking.
There's a higher percentage than 5 above the 4%.
okay, so if we calculated all these dots up, how many are there? Okay, I'm gonna go ahead and do it for you. 42 out of the 100. So that's 42%. 42% of this data is showing up here.
Yeah, it's greater than that.
So 42% of the time, we would get a difference of percent of 4% or more purely by chance. Okay. This is a hard concept to understand. It is. This is where a lot of people struggle. Okay. So with that being said, what I would suggest to you is 4.1 random recommended assignment, 4.2 recommended assignment. I'd go ahead and knock those two out and go ahead and start on 4.3. Okay. You need to spend time with this topic. It doesn't just miraculously get easy. Okay. Spend time with it. So with that being said, I'm also noticing a lot of us are still not on the AP Classroom thing. So if you have not joined, I'll put the join code up on the board in just a second. But a lot of you still have not joined.